This video is going to cover the classification of real numbers. We're going to start at the most basic set, which include the natural numbers. The natural numbers are given by the capital letter N and look like this in roster notation. Open brace and close brace, which depicts a set, and its members are 1, 2, 3, 4, and so on. These are the natural numbers, or the counting numbers. We call them counting numbers because you use them to count, like in hide and go seek. You start at 1 and continue from there. The natural numbers are comprised of two popular sets: the odd numbers, 1, 3, 5, 7, 9, and so on, and the even numbers, 2, 4, 6, 8, 10, and so on. Moving up one level, we have the whole numbers. The whole numbers differ from the natural numbers by only one member, a 0. So the whole numbers, when put in roster notation, look like this: 0, 1, 2, 3, and so on. You'll notice that the whole numbers are composed of the natural numbers and 0. So moving one step up, we have the integers. Now the integers in roster notation look like this. We go indefinitely to the left and indefinitely to the right, and these numbers are 0, 1, 2, and they include the opposites of the natural numbers, the negatives, -1, -2, -3, and so on. When you look at it graphically, you have the integers are composed of whole numbers as well as the opposites of the natural numbers. And what I mean by opposite is that we just change the sign. So 7 becomes -7, and 6 becomes -6. So the integers include the whole numbers, 0, 1, 2, 3, and so on, and the opposites of the natural numbers, -1, -2, -3, and so on. As we move higher on the hierarchy chain of real numbers, we stop next at the rational numbers, given by the capital letter Q. Now the rational numbers are going to be composed of all numbers that can be written as a ratio of two integers. So they're going to be composed of integers and then non-integer numbers. Well, what are these non-integer numbers? Well, they're going to be composed of any decimals that terminate or any decimals that repeat. Also, they're going to be fractions, because some fractions, when you turn them into decimals, they stop. Like 1/2 ends up being 0.5 as a decimal, and we consider 0.5 a terminating decimal because it stops. It has one digit, the 10th place, and then it stops. A repeating decimal you can get when you have a fraction like 2/3, because when you make that into a decimal, you get 0.6 repeating, 0.66666 forever and ever. This is considered a repeating decimal. Other repeating decimals could be something like 71/99, which would repeat 0.71 repeating, or 0.717171, and so on. So rational numbers are going to be any number that can be written as a ratio of two integers. We'll do some more examples later to hopefully clarify. The partner set of the rational numbers are the irrational numbers, denoted by the capital letter I. Irrational numbers are any number that cannot be written as a ratio of two integers. Typically, irrational numbers are going to be the square roots of numbers that are not perfect squares, like the square root of 2 and the square root of 5. It also includes numbers like pi. These are irrational because the decimals, they don't terminate and they don't repeat. There's no rhyme or reason to how the decimals continue. Rational numbers and irrational numbers combine to make the set of real numbers. Real numbers encompass all the numbers that we're going to use until probably the end of Algebra 2 when we start talking about complex and imaginary numbers. Let's look at some examples of some real numbers and how we can classify them. Our first example is a 5. Now a 5 is going to be a natural number because it falls under the set of 1, 2, 3, 4, 5, and so on. So we're going to put an in for natural number. Well, if it's a natural number, then it's also going to be a whole number, because the only difference between whole numbers and natural numbers is that whole numbers includes a 0. Again, if it's a set of the whole numbers, it will also be a set in the integers, which is denoted by a capital letter Z. And working our way up the chain, if it's an integer, it's also a rational number, because 5 can also be written as a ratio of two integers, as 5 over 1, or even 15 over 3, which simplifies to 5, or even negative 10 over negative 2, which also simplifies to 5. And if it's going to be a rational number, we know it's also going to be a real number. So 5 is a member of these 5 sets: natural numbers, whole numbers, integers, rational numbers, and real numbers. The next example we can look at is negative 6. Well, negative 6 is not going to be a natural number because it's negative, and natural numbers only include positive numbers. It also will not be a whole number because whole numbers start at 0 and continue upwards. So the first set that negative 6 is a part of is the set of integers. So we'll put a capital Z for integers. And again, if it's an integer, it's also a rational number because negative 6 can be written as many fractions, like 12 divided by negative 2, or 18 divided by negative 3. All those would be negative 6. And if it's rational, it's also going to be a real number. The next example that we're going to look at is 2/3. Well, 2/3 is not a natural number, and it's not a whole number. It's also not an integer because it's a fraction. So the first set that we can include it in is the set of rational numbers, because 2/3 is the ratio of two integers, the integers 2 and 3. So 2/3 we're going to say is a rational number. And if it's rational, it's also a real number. Here are some additional examples that we can classify using the real number system. Our first one is negative 7 over 9. Now negative 7 over 9 is a fraction, and a fraction in this case can be a rational number because a rational number is a ratio of two integers. In this case, our two integers are negative 7 and positive 9. So we can say this is going to be a rational number, and we denote that with the letter Q. And if it's rational, it's also real. Our next example is 0.3, or 3/10. Notice how you say that, 3/10, because as a fraction, this number is 3 over 10, 3/10. In this way, we can see that this number is going to be a rational number. It's a ratio of two integers. So we'll put a Q for a rational number and the R for a real number. Our next example is the square root of 2. Well, the square root of 2 cannot be written as the ratio of two integers. Whenever you put it into your calculator and take the square root of 2, you're going to get something like 1.414, and it's going to continue forever and ever with no rhyme or reason. So in this case, the square root of 2 is going to be irrational, and if it's irrational, it's also real. Let's classify 3 more additional numbers. The first one is 0.5 repeating. Any repeating decimal is going to be considered a rational number because this can be written as a ratio of two integers. In fact, 0.5 repeating can be written as 5 over 9. And if you were to divide that out and divide 9 into 5, you would see that you would get 0.555, and it would go on forever. So 0.5 repeating can be written as a ratio of two integers, so it's going to be a rational number. Rational numbers are given by Q, and we know if a number is rational, it's also real. Our next example is pi. And pi in decimal form is 3.14159, and it continues on, but with no rhyme or reason. So since there's no rhyme or reason to its decimals, it's going to be irrational, because we cannot write pi as a ratio of two integers. And if it's irrational, it's also going to be real. Our final example is the square root of 16. We have to be careful with this one, because we noticed in another example that square root of 2 was irrational. But the square root of 16 can be simplified because it's a perfect square. And the square root of 16 can be simplified to 4, because 4 times 4 makes 16. In this case, 4 is going to be a natural number, it's going to be a whole number, it's going to be an integer, it's going to be rational, and it's also going to be real.